Go ahead and start.
Cool.
Okay, great.
All right. So yeah, thanks everyone for coming, and thanks to the organizers for inviting me. So today, I guess I'll be continuing the theme of looking at how we do computation with lattices. And here we're going to focus on applications to commitments, signatures, and zero knowledge. And it turns out that all of these different primitives can be viewed through the lens of homomorphic commitments. Great. So in the last 25 years or so, we've seen a lot of different cryptographic constructions realized through lattice-based crypto, starting from, of course, Atai's seminal work on constructing one-way functions and collision resistance from the SIS function. And since then, there's been a number of works studying new types of functionalities that can all be realized from lattice-based assumptions. We saw public key encryption, then we got identity-based encryption, and in 2009, Craig Gentry gave the first construction of a fully homomorphic encryption scheme for the first time from lattice-based assumptions. And this has essentially opened up the floodgates of new constructions and instantiations from lattices. In the last 10 years, we've seen an incredibly prolific line of work showing how we can build things like attribute-based encryption, predicate encryption, constrained pseudo-random functions, notions like traitor tracing, and even non-interactive zero knowledge. All of these different notions can now be achieved from standard lattice assumptions. And in this talk, we're going to focus on a very, very small segment of this very general landscape. We're going to look at, in particular, homomorphic signatures and their applications to certain types of non-interactive zero knowledge. But it turns out that the machinery that we use, so these homomorphic trapdoor evaluation techniques that Hotek and Rotem have already pointed out and discussed, these can also be used to realize these types of applications. So without further ado, let me remind you what fully homomorphic encryption allows us to do. So in a fully homomorphic encryption scheme, the idea is we want some way of ensuring confidentiality together with computation. So what we can do is, let's say Bob here publishes a public key. Alice can encrypt any message of her choosing and delegate it to an untrusted cloud. And what the cloud can then do is take the encrypted message and directly compute to obtain an encryption of the function evaluated on the message. So the cloud can homomorphically compute on the ciphertexts. And at the end of that computation, Bob will get a ciphertext that encrypts f of x, which he can then decrypt using his secret key. So this is a way of delegating computation to an untrusted party while preserving the confidentiality for the inputs to the computation. Informally speaking, the properties that we might care about is security, namely semantic security for the message. The ciphertext hides the original message. And also, we want an efficiency guarantee, namely that the final output, the resulting ciphertext, only depends on the size of the output of the computation. And essentially, it's independent of the input size or even the size of the function. So is there a question? Oh, OK. So in all of throughout this entire talk, we will model functions as Boolean circuits. So when I say function, you can think about a Boolean circuit. So just as we can compute on encrypted data, we can also ask for a dual notion, which is, can we get integrity for computations, right? So we can view fully homomorphic encryption as providing some kind of confidentiality guarantee for a computation. We can also ask for an integrity guarantee. So in this setting, we can invert the roles of Alice and Bob. Let's say Alice has a signing key for a digital signature scheme, and Bob has a verification key. And what Alice can do now is she can take some input X. So you can imagine this could be a data set. Alice can sign that input and give it to the cloud. And the cloud will then compute some function on the signed data. And it can also produce a signature on the signed data so that when Bob receives the output consists of a function evaluation, the output of the function, so f of x, which is denoted y here, as well as a signature guaranteeing that this function was properly computed. So Bob can now verify a signature. And if the signature verifies, then he knows that the output y that he obtained is indeed the output of evaluating the function f on Alice's original data. So it's a way to provide integrity for computations. And just as in fully homomorphic encryption, we can define various properties we might care about. So security is going to essentially equate to unforgeability. So namely, if Alice signs an input x and the cloud computes a function f, then the cloud should only be able to convince Bob of the actual value f of x. It cannot reveal the signature for any value y prime that is not equal to f of x. So signatures are going to verify with respect to a value as well as a particular function. And similarly to fully homomorphic encryption, we also require a compactness property, which says that the signatures that are produced by the homomorphic evaluation procedure should be very short. It should only depend on the size of the output of the computation. It should not depend on the size of the input or the size of the function. So you can imagine that the inputs can be very large, the function can be very complicated, but if the output, let's say, is just a single bit, then the signatures should actually be much smaller than either the input or the function evaluation. All right, so how do we realize this? Well, the way that we're going to build this is starting from a fully homomorphic encryption scheme. So Hotek gave a really nice talk this morning on how we can realize fully homomorphic encryption. And in particular, he presented the construction by Gentry, Sahai, and Waters. So let me recall that construction here again. So in the Gentry, Sahai, Waters encryption scheme, the public key is an LWE matrix, namely the columns of A are going to be LWE samples. And the secret key essentially is the LWE secret. And the important property that we will use is this equation that Hotek also discussed, which is that if you take the inner product between the secret key and the public LWE matrix A, it essentially gives you something very small. So it gives you the noise term. The noise is assumed to be small. So this is approximately equal to the 0 vector. So this is one property that we will use in this talk. And so what does a ciphertext look like then? Well, the ciphertext is computed by, essentially it's a regef encryption. You take your public matrix A, you multiply it by a random short matrix R, and then you add to it X times G, where G here is the gadget matrix. So A times R is used to blind, and X times G is used to encode the message itself. So just to remind everyone, the gadget matrix here is, we'll use one particular gadget, which is the powers of 2 matrix. So you can view it as a rectangular matrix where you have the powers of 2 along the diagonal. The reason that we like this gadget matrix is essentially it's a matrix that has a public trapdoor. Namely, given any element in ZQ to the M, you can use this. You can use what's called the binary decomposition operator to sample a short preimage of the function itself. So namely, and we can extend this from vectors to matrices. So given any matrix A, G inverse of A basically takes the binary decomposition of the elements or the components of A. This gives you a short matrix such that when you multiply again by G, you recover the actual matrix A. Okay, so this will be very, very critical when we talk about homomorphic evaluation. Next, how do we decrypt? Well, decryption will use the fact that this is an LWE matrix. So if we multiply by S, you're going to get something short. You're going to get something that is small. So if we just multiply the ciphertext by the LWE secret S, notice that we get this S transpose A term, which will vanish just by how we set up the the public key. And we are left with X times S transpose times G. So G here is the gadget matrix. Another property of the gadget is that LWE is actually easy with respect to the gadget matrix. And so we can actually decrypt and recover the original message X. And throughout this entire talk, we can think about just encrypting bits of a message. So instead of encrypting a large ZQ element, we'll just encrypt bit by bit. It turns out that this is without loss of generality. Okay, so this is the syntax of the GSW encryption scheme. It's essentially just a version of regef encryption, but the interesting thing is that it supports a very expressive set of homomorphic operations. So just to remind everyone from Hotek's talk, we'll eventually end up at the single equation that Hotek derived. So just to see how where those equations come from with respect to the GSW encryption scheme, let's take a look. So suppose we have 2 ciphertexts. One of them encrypts X1. The second ciphertext encrypts the message X2. What we want to do now is we want to be able to construct ciphertexts that encode the sum or the product of these 2 ciphertexts. So let's start on the easy side. How do we compute an encryption of the sum of X1 and X2? Well, what we can do is we can simply add C1 plus C2. And notice now that C1 is an encryption of X1 with randomness R1, and C2 is an encryption of X2 with randomness R2. So if I simply add these 2 ciphertexts, everything adds, and we see that we get a new encryption of X1 plus X2 where the randomness is this function R1 plus R2. So if R1 and R2 are small to begin with, then their sum will be a little bit larger, but not by much. And so we still have a valid GSW ciphertext. So sum of ciphertext corresponds to an encryption of the sum. So second, we want to do multiplication. And multiplication is going to be a little slightly more complicated. Here we're going to make use of this G inverse function. So this is exactly the same multiplication relation that we saw earlier this morning. Namely, to multiply two ciphertexts, we apply G inverse to the second ciphertext and multiply it with C1. Why does this work? Well, let's just look at how the algebra lines up. So first, if C1 is AR1 plus X1 times G, we multiply AR1 by G inverse times C2. And then we have X1 times G inverse of C2. But by the properties of the gadget, G times G inverse will cancel out, and we're left with X1 times C2. So now if we just expand everything, we get very precisely another GSW ciphertext that encrypts the product X1 times X2, where the new encryption randomness is going to be, again, slightly larger, but not by much. Why is that? Well, if R1 is short and R2 is short, X is binary, so X1 times R2 is still small. And G inverse of C2, well, recall the reason that we like the G inverse function. The G inverse outputs binary valued matrices, right? It outputs matrices with small components. So if you multiply a short matrix by another short matrix, you're going to get something that is still short. And so we can now homomorphically also multiply ciphertexts together. Okay, so this is everything here is just a refresher from earlier this morning. So now let's see what the homomorphic operations look like. You can compose, once you have additions and multiplications, to evaluate an arbitrary Boolean circuit on the encrypted values. So given C1 up to Cn, there is an algorithm, basically by composing the addition and the multiplications, that gives us a new encryption, C sub f here, that encrypts f of x with respect to new randomness R sub f of x. And this is what I will call the input independent evaluation algorithm. And the reason why we distinguish it from a second equation, which is the main equation that Hotek mentioned, which is will depend on the input. Here, everything it only depends on the ciphertext, so the public value C1 up to Cn, as well as the description of the function f. And in fact, this is the whole appeal of fully homomorphic encryption, right? We can compute on the ciphertexts without knowledge of the message, right? So here I'm viewing the message as the input here. So this computation from C1 to C sub f, this only depends on components that are public. It only depends on ciphertexts and the function f. It is independent of the value x. So you do not need to know x to compute this quantity. All right. So with that, we basically have constructed a fully homomorphic encryption scheme, right? We showed how to do homomorphic addition and homomorphic multiplication. We've shown these algebraic transformations that induce a corresponding homomorphism on the message space itself. So a natural question to ask is this all that we have from this scheme, right? And the very amazing thing about the GSW encryption scheme is that there is a second homomorphism that we're implicitly using. So we didn't explicitly use it here, but if we look at it more closely, and especially when we look at the security analysis, we see that there is actually one additional source of homomorphism. Not only are we homomorphically computing on the messages, there is also a homomorphism on the randomness, on the encryption randomness itself. And the key observation here, and this is needed for even a correctness analysis of GSW, is that when we do these homomorphic operations, we derive new ciphertexts with respect to a new set of encryption randomness. And the new encryption randomness is actually a short linear combination of the original encryption randomness R1 and R2. So where the short linear combination can have coefficients that depend on the input x, as well as the ciphertext C1 up to Cn. So what does that mean? So this was first formalized and extracted and used to construct attribute-based encryption in a work of Bonnet et al., where basically this homomorphism says the following. There's a public homomorphism that takes the ciphertext and produces a ciphertext that encrypts f of x. But what about the encryption randomness of this new ciphertext, this R sub f of x? Well, R here can be expressed as a linear function of the original R1s up to Rn. And what is that linear function? Well, it is precisely this function h sub f and x. So this is exactly the same H matrix that Hotek had in his talk. So it's it just falls out for free from the GSW homomorphisms. And a very important property that we also exploited to argue correctness of the GSW is that this matrix here is very short. So namely, if you start with a valid GSW ciphertext, you have short matrices R1 up to Rn. If you multiply by another short matrix, then R is still short, and decryption will still succeed. So now let's actually try and recover the actual equation that we saw earlier today. It basically falls from just rearranging the terms, right? So we can left multiply this equation right here by A. So we get A times everything equals A times R sub f of x. And notice that AR1 and ARN are precisely related to the actual ciphertext themselves, right? So we can just replace AR1 with, say, C1 minus X1G, and so on. And so we now recover the second equation that we saw this morning. And this equation I will refer to as the input-dependent evaluation algorithm. So given matrices C1 and up to Cn, a function f, and an input x, we can construct this matrix H sub f of x such that this particular relation holds, right? So I just want to contrast it with these two relations. So the first relation says I take a sequence of matrices and I take a function f, but nothing about an input x, and I can construct C sub f. Here, I have a sequence of matrices. I have f and I have x as well, and I can multiply by this matrix H sub fx. That will produce C sub f, the same C sub f as in the first equation, but minus the evaluation here. And it turns out that these two homomorphisms actually give us a lot of power and has been used in many settings to realize many different kinds of lattice-based instantiations. So I guess I have the same table that Hotek had at the beginning of today. So essentially, we can use these two homomorphisms to realize things like attribute-based encryption. This is what Rotem described in her previous talk. We can use them to get homomorphic signatures. We can use them to get constrained pseudo-random functions. And essentially, in each of these constructions, one of the algorithms, so for instance, key generation in ABE, will use one of these homomorphisms. And a different algorithm, for instance, decryption, will use the second homomorphism. And they're tied together by this fixed matrix C sub f. So in this talk, we're going to look at the homomorphic signature application, which also uses the same underlying techniques and ideas. All right, so we're going to view everything conveniently through the lens of a homomorphic commitment. And it turns out this view is actually quite useful. It allows us to get certain kinds of zero knowledge. It also allows us to get homomorphic signatures almost for free, which I will describe at the very end of this talk. So for the most of this talk, we will just view everything through the lens of a homomorphic commitment. And luckily for us, the GSW encryption scheme already gives us a homomorphic commitment. So there's nothing more that we have to do. And why is that? Well, let's take a look at a GSW ciphertext, right? So here we have a GSW ciphertext that encrypts the value x. So C equals A times R plus X times G. So what we can view is C here will be a commitment. X will view as the message that we are committing to. So what is the commitment opening? Well, that will precisely be the encryption randomness. So this is not very surprising, right? If you have a public key encryption scheme that is committing, that immediately gives you a commitment scheme where the commitment opening is the randomness used in the public key encryption scheme. So GSW has those properties, and we can reinterpret or just simply sort of view GSW as implementing a commitment scheme where the encryption randomness itself is the opening. Okay, so instead of viewing C as an encryption of X with randomness R, we can equivalently view it as a commitment to X with an opening R. And to check the opening, we simply verify that it is short and that this relation holds. So this commitment scheme has several nice properties. First, it is statistically binding. This follows by correctness of GSW. And in fact, it is actually an extractable commitment scheme, right? Because GSW is an encryption scheme. If you know the secret key, you can actually decrypt. You can actually recover the message. So extractability immediately gives you the statistical binding property. And next, it is also computationally hiding. This is exactly semantic security of the encryption scheme, right? The commitment scheme is literally an encryption of the committed message itself. So computational hiding or security of GSW which follows under the standard LWE assumption that ensures that this commitment scheme is hiding. Okay, so once we have this commitment scheme, we know that this is exactly GSW. I've done nothing fancy yet. I've just been redefining things essentially, or moving things around. Well, it inherits all of the properties of the GSW encryption scheme, namely, it is a homomorphic commitment. So what that means is the following. Suppose that I commit to values x1 up to xn, right? So here we have the GSW.
David, sorry to interrupt, a question. So what about dishonest generation of the public key? Then David's not going to be committing.
Great. Yeah, that's an excellent question. So this is a commitment scheme in a CRS model. So we assume that the public key is honestly generated.
Thanks.
Yeah, so basically there's a setup algorithm that publishes the public key. In this case, the public key will have to be an LWE matrix. And if the public key is actually malformed or generated with knowledge of a trapdoor, then both of these properties may not hold anymore. Yeah, so this is a commitment in a CRS model. Excellent question. Okay, great. So what does the homomorphic properties allow us to do? So suppose we have commitments to the bits of x1 up to xn. What we can hope for, or we can use a homomorphic commitment to achieve, is we can now open this commitment to any function of f of x, right? So in a standard commitment scheme, we have a commitment to a message, and we can open a commitment to that message. In a homomorphic commitment scheme,
you have one more question?
Oh, yeah.
I want to try that.
Oh, can you explain under which assumption is the commitment scheme extractable? So this is, extractability is an information theoretic property. So basically, if the matrix A is correctly sampled, namely it is this LWE matrix, then the LWE secret key there actually gives you an extraction trapdoor. So this is an information theoretic property, assuming that the matrix A was sampled correctly. Can this be a dual mode commitment? Good. So yes, indeed, this is a dual mode commitment. This we will come back to at the very end of this talk when we say how to get homomorphic signatures. So, just to foreshadow, let's say something half an hour from now, we will say that when A is a uniform random matrix A, we can sample A with knowledge of a trapdoor. The trapdoor will allow us to build an equivocable commitment scheme. Namely, you can open commitments both to 0 and 1. And it turns out that an equivocable homomorphic commitment gives you a homomorphic signature. So that will require a little bit more tools. We will have to talk about lattice trapdoors, but we will get there at the very end of this talk. Excellent question. Okay, so back to homomorphism on the commitment scheme itself. So a homomorphic commitment says I can commit to a value x, and then I can homomorphically evaluate on those commitments, and then open the commitment to a function of the original value, right? So here I committed to x, and suppose I want to open a commitment to a function f evaluated on x. So the syntax here will be the following. So the open algorithm will take in the public parameters. So just going back to Ram's question, we have a common reference string or a CRS. The public parameters is that CRS. It takes in a commitment, and then it takes in a function, and then the value, and it takes in the commitment opening. And it tells you, and it just basically checks whether this opening is a valid for evaluating this function on a commitment to obtain this value. So what the binding property says is the following. We cannot open a commitment with respect to the same function, but have two different values, right? So the standard binding property says that we cannot open a commitment to two different values. Here we have a homomorphic commitment, so you can evaluate any function on the values themselves. So when we define the binding property, we also define it with respect to a function f. And we say, once you choose a function f, there's only one value for which you can open up the commitment. The correctness property will say that you can, if you have a commitment to x and you evaluate the function f, you can open it to f of x. So this basically says you can only essentially open a commitment to y equals f of x. And the application that I will describe of this is basically a notion of non-interactive zero knowledge. It doesn't give you fully non-interactive zero knowledge in the usual sense. It gives it to you in a weaker model called the preprocessing model, which I will introduce very shortly. So before we do that, before we talk about the application to non-interactive zero knowledge, let me just make sure it is clear how these homomorphic operations actually happen and how we open up these kinds of commitments. So on the left here, I have my homomorphic commitments to the bits of the input x. And so given the commitment C1 up to Cn, without knowledge of the committed values, I can compute a commitment to f of x, right? So this is the public evaluation algorithm. This is just ciphertext evaluation in a GSW encryption scheme. So if we look at the structure of this commitment, well, it's a commitment to f of x, where what is the opening? The opening is the new encryption randomness after performing a homomorphic evaluation. So from the perspective of a user who commits to an input x, how does that user open a commitment? Well, they precisely use the ciphertext evaluation or the input dependent evaluation procedure. So they have the openings to the original commitments, R1 up to Rn. And if they want to open a commitment to a function f, basically, they will just multiply by this H matrix here. And this will produce the new commitment opening. So how does a verifier check that a commitment was opened correctly? Well, the verifier can compute the commitment to f of x, and then it just checks whether this opening satisfies the original commitment relation and that this opening is short. So with these properties, just to remind you, these are the two main evaluation criterions. The verifier that checks the commitment opening is going to use the public algorithm. To compute the opening, we're going to use the secret algorithm. Okay, so this gives us a homomorphic commitment, and we can open up the commitments very efficiently. So how do we go from commitments to proofs, right? So I'm going to now describe an application of homomorphic commitments to constructing certain types of non-interactive zero knowledge from standard lattice assumptions. So at a very high level, the idea of why commitments seems to be connected to proofs is, suppose we have the following setting. We have a prover, we have a verifier, and the prover wants to convince the verifier that some secret statement X satisfies some relation R, right? So this is still a hypothetical scenario. We'll bring it back to non-interactive zero knowledge for MP very shortly. So how might we use a commitment to facilitate this kind of protocol? Well, one thing we can consider doing is we can have the prover commit to a value X with respect to some public parameters. So we'll assume that there is some common reference string. So there was some setup that generated this common reference string. And now the prover wants to convince the verifier that X satisfies some property. So the prover will commit to X. The commitment is hiding, so this hides X. And now if the prover wants to tell the verifier that this statement is true, it can compute an opening to the commitment of the relation evaluated on X, right? So if it wants to prove that some relation or some predicate holds for the secret value X, instead of opening X, it can open the value of the predicate evaluated on X. And essentially, we can view that this opening is almost a proof that the commitment or that this relation holds for this particular statement. So there's quite a few details I'm sweeping under the rug. So this does not work by itself. We'll patch it eventually. But this is just sort of the intuition for why there's a flavor of some kind of proof system already implicit in a notion of a homomorphic commitment. What does the verifier do to check? Well, if it wants to check that the statement X satisfies this relation, it can take the commitment to X, evaluate this relation on it. So the relation we assume is public. Then it derives a commitment to R of X. And now it's going to check that the prover actually provided a valid opening to R of X. So if R of X equals 1, and this is an opening to 1, then the verifier accepts. Otherwise, the verifier rejects. OK, so how can we use this basic intuition and actually derive from it a zero knowledge proof system? So let's try and build non-interactive zero knowledge directly from this observation. So take your favorite NP relation. So here I'll denote it R. So it takes the statement, takes the witness. And suppose we want to, the prover's goal is to convince the verifier that the statement X is true without revealing any information about the witness. So I didn't define zero knowledge here, but zero knowledge basically says that whatever the prover sends to the verifier, there exists an efficient simulator that can simulate the proof given only knowledge of the statement and nothing more. Okay, so how might we use a homomorphic commitment to implement this kind is to get some kind of non-interactive zero knowledge like object? Well, a simple idea might be something like the following. We'll assume that we have a common reference string, which will be the public parameters for the commitment scheme. And we'll say, well, the prover is going to commit to the witness for X, right? So the prover is assumed to know the witness. The prover will commit to it. If the commitment scheme is hiding, this should hide the commitment. This should hide the actual witness. And now, how does the prover convince the verifier that indeed this is a valid witness? Well, it can compute this function, basically the MP relation, that has a statement X hardwired inside it, right? So this is now a function that only depends on a witness. It has X hardwired inside it. And notice that this is a function that the verifier knows, right? The verifier knows what statement is being proved. So the verifier can compute this function. So what the verifier can do now is it can evaluate homomorphically this MP relation on the commitment itself. And that will produce a commitment of the MP relation evaluated on X and the committed witness W. And the verifier will simply check that this is indeed a commitment to the value 1. So let's take a look at the properties of this strawman protocol. So let's first look at zero knowledge. So zero knowledge at a very high level, so minimally, it says that the proof better hide the witness W. So why would this hold for this protocol here? Well, first we know the commitment is hiding. So if the commitment scheme is computationally hiding, then this commitment here cannot reveal any information about the witness W. We can replace it with a commitment to the all zero string, for instance, and this will be computationally indistinguishable. So for computational zero knowledge, this seems okay. And then we also need to argue that this opening of the commitment scheme also does not leak information about W. So this is not a property that is true right now. It turns out that this can be fixed. So just take my word for it for now. At the end of this talk, I will say how exactly we fix this. But for now, I will just say that there is a way to open the commitment in a way that only reveals information about the evaluation, so of the committed value, but does not reveal information about the original commitment itself. So namely, this commitment here, this opening, can be simulated just given the MP relation evaluated on a witness and does not leak information about the original witness itself. So it's exactly the zero knowledge relation. So this protocol, as I described it here, can actually be shown to provide zero knowledge. Unfortunately, though, soundness is what breaks. So soundness, intuitively, we want it to follow for the following reason. Suppose that in the first message, the prover generates a commitment to some value. Okay, so it is some honestly generated commitment. If that is true, and X is a false statement, then this function that we are going to compute, this MP relation with X hardwired inside it, this is the identically zero function. Yeah, so if it is the identically zero function, then when the verifier computes on this commitment C sub W, is computing the identically zero function. And so this commitment that the prover produces is always a commitment to zero. And if the commitment scheme is statistically binding, then we get statistical soundness of this proof system. So if the commitment was correctly generated, it is actually a commitment to some value W star, then this protocol would actually give you a statistically sound proof system. Namely, because the prover is computing the identically zero function on the committed value, and in order to convince the verifier, it has to open a commitment to zero to the value 1, which it cannot do. Unfortunately, though, this is assuming something very, very strong, namely that this commitment scheme is honestly generated. And unfortunately, we do not know today how to construct how to have a mechanism to guarantee that the commitment scheme is honestly generated. So here's a very interesting open problem. Can we construct a non-interactive zero knowledge proof that says that a regef ciphertext or a GSW ciphertext is well formed? Namely, given a ciphertext and a public parameters, there exists a short matrix R as well as a bit X such that this is a valid ciphertext.
Can I ask a question?
Yeah.
Just to make sure that I'm following here. So you're now in a setting where supposedly the prover wants to cheat. I mean, you're checking soundness, right?
Yes, that's right.
And you're saying, so he's a cheater. Why would you assume that he generated a commitment to something that's not a witness in an honest way, right? That doesn't make sense. But if somehow this cheating prover was forced to at least do this step honestly, then we would be okay.
Yes, then yes. So if we can guarantee that the initial commitment is actually a well-formed commitment to something, then we can appeal to statistical binding of the commitment scheme to argue that the proof system is statistically sound.
Good. Okay.
Right. But if the prover does not generate this commitment in the honest way, then we have no guarantees.
Mm-hmm. Good.
So one more
Yep.
question.
So this sort of motivates the study of, can we build a non-interactive zero knowledge?
There was another question, I think.
Yeah.
That's me, Daniele. So so what do you mean? So what do you need to show in order to show that a commitment is correct? Isn't this just a proof for an instance of the bounded distance decoding problem?
That's right. It is. So a NIZK proof for the bounded distance decoding problem, I think, would also suffice to show NIZK for NP.
But isn't this something that is known, at least for sufficiently large values of the parameters? We know that
so I'm not
there are
sure
interactive proofs and also non-interactive. I think it should be a fairly.
I'm not aware that there is a result that gives us a NIZK for BDD where we have an efficient prover.
So this is Vinod. There is a NIZK for the complement of this language. In fact, a statistical NIZK. But we don't know a NIZK for this language. I mean, we now know it from LWE,
sure.
all the recent works on Fiat-Shamir.
Right, through Fiat-Shamir, we can
then we know it. But before that, if you rewind to 2018, I suppose you don't know it.
Can I ask again a question, clarification? So the commitment is a commitment, right? So it's still binding. So that, you know, a cheating prover will not be able to generate a commitment that you can open both ways. Mm-hmm. So what is the difference here? So what is the difference for that particular commitment?
Yeah, so in order to argue soundness, there were actually two steps, right? So if the commitment was indeed a valid commitment, then after you perform the homomorphic evaluation, that evaluated commitment will always be a commitment to zero. But if you don't have a valid commitment to start with, then when you perform the homomorphic evaluation, you can't argue that you always get a commitment to zero. It's possible that you get a commitment.
But a commitment is a matrix, right? Which is
right. That's right.
Yeah.
Yeah, but you may not be able to resolve it directly to a particular value. Like there's no binding property if the commitment is not well formed.
David, there's a couple of questions from the system. You can decide whether you want to hit them now or if you think timing wise it's better to move on.
Okay. Yeah, so maybe we should move on, and then I can take some of the more questions about the commitment offline afterwards. Okay, right. So just to sort of motivate this problem, if we have a simple NIZK or a direct construction of a NIZK for this setting, we can actually get a direct construction of non-interactive zero knowledge for MP. And this would essentially, assuming that this NIZK here, it makes only black box use of crypto, then we would get a construction of non-interactive zero knowledge for general MP languages from lattices that doesn't need to make non-black box use of crypto. So the beautiful Fiat-Shamir approach gives us a NIZK for general MP languages from LWE, but it does require evaluating the hash function on a cryptographic object. Okay, all right. So here we sort of suggested this dream version of if we had this way of proving that the commitment is well formed, then we can actually leverage this homomorphic commitment to build some kind of zero knowledge proof. But we don't know how to realize this. So the natural next question to ask is, well, can we still use this approach to get some kind of zero knowledge system? And the answer turns out to be yes, but we have to relax the model a little bit. So instead of working in a standard CRS model, we will have to work in what's called a weaker preprocessing or correlated randomness model. So let me introduce this model and then say how we can patch the construction. So in the preprocessing model or the correlated randomness model, we're going to assume that there is a trusted setup that comes at the beginning of time, and it generates a proving key and a verification key. And it gives the proving key to the prover, it gives the verification key to the verifier. And thereafter, the prover can generate proofs of arbitrary statements and witnesses with respect to the proving key, and the verifier can use its verification key to actually check the proofs. So Importantly, this is a relaxation of the common reference string model in the following sense. This is simpler because we only require soundness to hold, assuming the verification key is hidden. So the verifier has a secret, the prover has a secret, and we're assuming that the soundness will hold against the prover that doesn't know the verification key, and correspondingly, zero knowledge doesn't hold, assuming that the verifier does not know the proving key. So both the prover and the verifier have secret state. So we can view the CRS model as the case where both the proving keys and the verification keys are public and part of the common reference string. In this case, in a preprocessing case setting, they each have a secret proving and verification key. So the main requirement that makes this model still interesting is it should be reusable. Namely, the setup algorithm should only have to be done once, and it generates a proving key and a verification key for the prover and verifier respectively. And thereafter, they can prove an arbitrary unbounded polynomial number of statements without needing to run the setup algorithm again. So in many multi-party computation settings, this actually suffices for those types of applications of zero knowledge. Okay, so how do we use, how can we take this general protocol and use it to get a zero knowledge proof in this model? Right? So the challenge that we had ran into before is that we did not know how to prove that this commitment is a valid commitment, right? That there is some value that is associated with it. So what do we do? Well, let's consider the following strawman approach. We want this to be a valid commitment, then everything else follows. So if we don't know how to have the prover prove that it knows that this is a valid commitment, we will instead move this proof to the trusted party. So suppose for a moment that the trusted setup is going to generate the commitment to the witness as well as the opening. And now we don't have to worry about the commitment being well-formed or not. It's generated by a trusted party, is assumed to be well-formed. And the verifier has this commitment. And so all we have to do now is have the prover output the opening to the MP relation. So evaluate the opening to the MP relation evaluated on the committed witness. So now this avoids the soundness problem. We sort of assume that because the trusted party generates the original commitments, we don't have to worry about proving that those commitments are well formed. So that part of the protocol is fixed, but we run into a different problem now. The preprocessing here, notice, is now witness dependent. Namely, this trusted party, what it generates at the beginning of the protocol is actually something that depends on the statement being proved, right? And we wanted this trusted party to be a one-time setup process, and it should be completely statement independent. It should not know about what statement or what witness is being used. In particular, if the prover has to go to the trusted party to get a commitment to the witness every time it wants to prove a statement, this is no longer a non-interactive protocol. So to address this problem, it suffices to just add one additional layer of indirection. So the key idea now is the following. Instead of giving a prover a commitment to the actual witness, we're instead going to give the prover a commitment to an encryption key K, and the prover will also be given the opening to this encryption key K. Okay? And the verifier is just given the commitment to the key K. And now, why is this useful? So the first thing I want to note is that this preprocessing now is completely statement independent, right? It just samples a random key K, and the prover is given an honestly generated commitment to this key K. So to actually generate a proof of some MP statement now, what the prover would do is it would first encrypt the witness using the key K. So the prover knows this encryption key. The prover will encrypt the witness using the key. And now what does it do? It's going to generate an opening for this function f that has the statement x and this ciphertext, this encrypted witness, hardwired inside it. And what this function f does is it takes as input, first of all, the decryption key, and it basically takes the key, uses it to decrypt the associated ciphertext, and then evaluates the MP relation on the statement and the witness pair. Okay, so this function has the statement x and a ciphertext hardwired inside it. It takes in a key as input, uses the key to decrypt the ciphertext to obtain a witness, and then uses the witness to check the MP relation. So this is essentially just checking the MP relation on an encrypted witness. So notice that this function here, the specification of this function, is entirely public and only depends on quantities known to the verifier. Namely, the verifier knows the statement and it knows the ciphertext. So it can compute this function f here. So the verifier can take the commitment to the key k and homomorphically evaluate this NP relation checking function on this commitment. And then it checks that the prover can actually open this commitment to the value 1. So why is this protocol now sound? Notice that if the statement is false, then this function f here is the identically 0 function, because the function f computes the output of the NP relation, where for a false statement x, by definition, there is no input that will cause the NP relation to output 1. So as long as we have a valid commitment to the key k, which we do, that's generated at the setup time, then once we evaluate this function f on that commitment, we get a commitment to 0. And so now soundness follows by statistical binding of the commitment scheme. The prover cannot open a commitment 0 to the commitment of the value 1. Why does zero knowledge hold? Well, zero knowledge holds assuming that the commitment hides the key k, and the opening also hides k. So again, we have this caveat where we need that this opening is also zero knowledge, that it doesn't leak information about the key. So again, I'll sweep this detail under the rug. We will revisit it in a few minutes, in a couple slides. But if we assume that the commitment scheme and the opening hides the encryption key k, well then the ciphertext that encrypts the witness will hide the witness by semantic security of the underlying encryption scheme. Right? So essentially, instead of committing to the witness, it suffices that we can commit to a key. And if we can commit to a key, then we can actually build a non-interactive zero knowledge in this setting. So the overall non-interactive zero knowledge scheme in the pre-processing model then works as follows. So the setup phase basically just generates a commitment to a key k, as well as the encryption key, and the prover secret key is the opening, and the verification key is just a commitment. And in fact, if we look at this picture, notice that the verification key is this commitment, and this commitment is also known to the prover. So there's no reason that the verification key has to be secret. So everything I described here can actually be used to construct a publicly verifiable proof system where the prover has a secret key. So for this reason, we call it a designated prover non-interactive zero knowledge from homomorphic commitments. So this is sort of like a dual of the designated verifier setting. So designated verifier means there's a secret verification key. In the designated prover setting, there's a public verification key. So anybody can check proofs, but only a designated prover can generate proofs. Okay, so any questions before we move on? So I'm going to talk about how we get that zero knowledge property. So does it matter what encryption scheme we use? So this general framework is agnostic to the choice of encryption scheme. So any semantically secure encryption scheme will suffice. It does matter when we talk about the parameters. So if you have an encryption scheme with low depth, then we can actually use a homomorphic commitment that supports low depth computations. So it does matter in the terms of what assumptions and what parameters we use that we get from the final instantiation, but the general framework is agnostic to the choice of encryption scheme.
David, this is Hotek. Does the framework have a dual mode version, or is it inherently you need the commitment to be statistically binding?
So you can switch the commit. So the commitment is dual mode. You can switch the commitment to a homomorphic signature, but then you lose the soundness. Soundness gets downgraded to computational soundness, and zero knowledge is still computational because of the encryption scheme. So there is a dual mode, but it seems like it's a strictly worse. So the commitment scheme gives you statistical soundness. With a signature scheme, you get computational soundness and computational zero knowledge, because we're still relying on an encryption scheme to hide the witness.
But you can imagine some kind of dual mode encryption, right? Is that then sufficient to compose to give you dual mode preprocessing, is it?
Yeah, that's a good question. I have to think about that a bit. I don't think it, so when we were trying to do this, I don't think it gave us a direct approach. So I think the best we can do from this technique right now is statistical soundness, computational zero knowledge. And it's not clear to me that we can get the full dual mode. Yeah, but it's an excellent direction. Can you repeat where RK is used by P in the proof? Good. So RK, recall, is the opening to the commitment to the key K. And what is the proof? So if we look at it, the proof is an opening to the function f evaluated on a committed key. So recall that to compute an opening to a commit, evaluate the function h, or we multiply by the matrix h sub f of x. So that's where RK is used. Okay, great. Okay, so there's a few more details that I've swept under the rug. So let's come back to those details, and that will also give us homomorphic signatures as a byproduct. So recall that the requirement for zero knowledge is that the opening to the commitment scheme hides the committed value up to what is revealed by the function of x, right? So in this case, the function, in this case, x in our zero knowledge construction, x is the secret key, f of x is the MP relation, right? So the MP relation, it just outputs 1 if the statement is true. We don't want to reveal information about the key. So this is not true as written, because if you look at how the opening is computed, it's a function that depends on x, as well as the original openings to the commitments themselves. So as written, this can leak a lot of information about R1 up to Rn. So this by itself is not context hiding. So what I mean by context hiding then, so I'll give an informal definition for the sake of time. We basically want to ensure that the public parameters, this matrix A here, as well as the commitments and the openings, can be simulated given only the function that we computed and the function value f of x. So given only f and f of x, we should be able to simulate the public parameters, the commitments, and the openings. In particular, we do not require knowledge of x. So this has a very zero knowledge flavor, has a very MPC flavor type of definition. So in order to realize this, we will need one more ingredient. So we will need the notion of a lattice trapdoor. And I'm not going to go into details here. I think Shweta gave a really nice talk at the first Lattice bootcamp on how these gadget trapdoors are constructed and how they operate. So I'll just describe the main properties we care about. So here we will just use the gadget trapdoors by Daniele and Chris, which basically a trapdoor for a matrix A is a short matrix R such that A times R is equal to this gadget. And it turns out that this trapdoor has many useful properties. One property that we will use here is that it enables us to sample pre-images under the SIS function. So here we have the SIS function, takes in a vector x and computes the product A times x over ZQ. So what a trapdoor for A allows us to do is it says, given some element that's in the range of this function, and if you choose the parameters accordingly, this is a surjective function, in which case you can say, given any element in the codomain, and the lattice trapdoor R, we can actually sample a pre-image such that A times x prime is equal to U. And the important property of this is that this pre-image is actually Gaussian distributed over the set of solutions to A times x equals U. Okay, so in particular, there's a very nice Gaussian distributed distribution over the solutions that we are sampling. So this is the only property that we will rely on here. So the second thing I want to point out is, suppose now that we have a matrix A, and the matrix A is the concatenation of two matrices A1 and A2. It turns out that there are actually many possible trapdoors for this matrix A. I will just describe two of them that turn out to be very useful. So suppose first that we have a trapdoor for A1, right? What does that mean? That means I know that A1 times R1 equals the gadget. Then we can actually extend this trapdoor to a trapdoor for any extension of A1. So in particular, if I just concatenate 0, I still have a useful trapdoor for the concatenation of A1 and A2. Right? So it suffices that I know a trapdoor for a sub matrix. That's the first observation. And the second observation that I want to make is that there's another way that we can come up with a trapdoor for this matrix A, which is if we know that A2 is a short linear combination of A1 plus the gadget matrix, then R2, this short matrix here, can also be used as a trapdoor for A. Namely, we just take R2 and the identity matrix here, and once again, we get the gadget matrix G. So whenever we have, if we have a trapdoor for the matrix A, now we can use this pre-image sampling idea to sample pre-images of any target vector U so that they're distributed in a Gaussian way over the lattice or over the set of solutions where AX equals U. And so there are two ways of sampling from this particular distribution. And whenever you have two ways of sampling from a common distribution, that oftentimes is very useful for cryptographic applications. In particular, we will use one of these methods to sample in a real system and one of these methods to sample in a simulation. So let's take a look at how we can apply these techniques to the setting to get a context-hiding homomorphic commitment. So to simplify things, I will just describe how we handle the case where we can only open commitments to the value 1. So if you have a commitment to 0, you can't open it. If you have a commitment to the value 1, then you are able to open it. Notice that this already suffices for zero knowledge, because in zero knowledge, we only open commitments that actually satisfy the NP relation. If you want to consider general functions, there are many ways to do it. A simple way is, instead of evaluating the function f, we can evaluate the complement of f. At least one of them will have the value 1. OK, so why is this useful now? So suppose I have a commitment to the value 1. That means that this matrix A concatenated with C sub f, when we evaluate this by the GSW evaluation, f of x equals 1, I get A times R plus G. And moreover, R here, the opening to the commitment, is short. So what does this mean? So if we have a trapdoor for A, we can sample short preimages in this lattice, right? Or if we know the opening to this commitment, and it is a commitment to 1, namely we know this R sub f of x here, then the committer also has a trapdoor for this common matrix. So what we're going to do is we're going to include a random target vector u in the public parameters, and the opening is going to be a short preimage such that A concatenated with the evaluated commitment times V is equal to u. Okay, so if we have a commitment to 1, we can sample this preimage by using a trapdoor based on R sub f. And if in a simulation we don't know what this value is, but we know what A is. If we have a trapdoor for A, we can also sample the preimage V. So let's just look at what the scheme looks like now. So in the real scheme, we have our public parameters, which is the LWE matrix A, and we have a random target vector U. The commitment is just GSW encryptions of the input. And to open, what we do is we homomorphically evaluate the function f on the commitments, and that will give us a matrix C sub f. And then we sample a preimage in this target lattice defined by C sub f. And the way we do so is we use the trapdoor that we get, which is the commitment opening itself. How do we simulate this? Right. So now the simulator, notice, is only given f and f of x. So the first thing we're going to do is we want you to give the simulator a trapdoor for A. So it better be the case that A actually has a trapdoor. So it can't be an LWE matrix. But luckily for us, under the LWE assumption, the LWE matrix A is indistinguishable from a uniform random matrix A, for which we can sample a trapdoor for. Right. So instead of sampling an LWE matrix, we're going to sample a uniform random matrix here. Now, how do we choose the commitments? We don't know xi here, but here we can just sample a uniform random matrix C. The reason we can do this is because if A is a uniform random matrix, R is short and has enough entropy, we can appeal to the leftover hash lemma and say that A times R is actually uniform, and this is a one-time pad blinding of xi times g. So the commitments can just be random matrices. They do not depend on the input x. And finally, how do we simulate the openings? Well, we can compute the target lattice defined by C sub f just by computing on the commitments. That gives me, just by evaluating on the commitments, that gives me C sub f. And now what is an actual opening? Well, it's a short preimage of u, is a short preimage v such that A times C sub f times v is equal to u. And because we sampled A using knowledge with a trapdoor, we can use our trapdoor to sample this accordingly. And so notice now that in a simulation, everything only depends on the value f of x and not x itself. Okay, so going back to the question about there's a dual mode property. So if we look at this context hiding transformation, we notice that in the simulation, we switched the matrix A from LWE matrix to a uniform random matrix A. It turns out that this notion by itself is already also very useful. So if A is uniformly random, we can have a trapdoor. And if we have a trapdoor, we can actually turn this into an equivocable commitment scheme. Namely, right. So this is equivocable because if you have a trapdoor for A, you can sample a short R such that A times R is equal to C, or A times R is equal to C minus X times G. Right? This is exactly the property that we're exploiting in a simulation. Like, we don't know what the value of X is, but it doesn't matter. We can still simulate the value for f of x by using this equivocation trapdoor. And moreover, if A is a uniform random matrix here, we can switch A to an LWE matrix. This will give us a computationally binding commitment scheme, right? Because here, if A we know is LWE matrix, we know it's statistically binding. So if we can switch from a uniform random to LWE, then we get a computationally binding commitment scheme. I think I'm running out of time, so let me just briefly introduce homomorphic signatures. So we're basically there. So if we have a uniform random matrix A here, we said that this commitment scheme is equivocable. Namely, you can actually sample openings to both commitments to 0 as well as commitments to 1. This equivocation trapdoor can be used to obtain a signature. So the verification key in this case for the signature scheme is just a random matrix A with the knowledge of a trapdoor, as well as C1 up to Cn. And the signing key is exactly a trapdoor for this matrix A. So just to be very brief, so the verification key is exactly the same as before, except we just have random target matrices. And the signature is essentially the same as a commitment, except the openings to the commitment now correspond to the signatures. We can now compute on signatures, because signatures are commitments, is exactly the same GSW evaluation procedure. We compute on the openings or the signatures, and that gives us a signature on f of x. So to verify now a signature, anyone can take the verification key, take the function. This defines the target, C sub f, and they simply need to check that A times R plus f of x times g is equal to C sub f. So unforgeability now follows from the binding property of the commitment scheme. So if this commitment scheme is computationally binding, we get computational unforgeability. Okay, so just to summarize, everything I talked about in this talk really boils down to understanding and analyzing the structure of GSW ciphertexts, and in particular, interpreting or viewing GSW ciphertexts as a homomorphic commitment scheme. So the GSW ciphertext has a remarkable amount of homomorphism. In particular, we have these two master equations. One of them tells us how to evaluate just on the commitments or the ciphertexts. The other one depends on the inputs and gives us a way to derive relations between evaluating on the public components and evaluating on the secret components. And the two different methods of instantiating this commitment scheme. So for instance, if A is an LWE matrix, then we get extractable commitments, so statistically binding, computationally binding. If A is a uniform matrix, that gives us an equivocable commitment, which also gives us homomorphic signatures. And in both of these cases, both homomorphic commitments and homomorphic signatures, they allow us to build designated prover non-interactive zero knowledge. So let me conclude with a few open problems. So I mentioned the first one, can we have a NIZK proof of well-formedness of GSW ciphertext without going through Fiat-Shamir? So I should clarify that given recent advancements using Fiat-Shamir. Can we do it more directly, right? Can we do it without making non-black box use of crypto? But there's also several questions related to homomorphic signatures and commitments that I want to highlight. So a very interesting question here is, can we have fully homomorphic commitments or fully homomorphic signatures from lattices? So in the case of homomorphic encryption, if we assume circular security, we can actually get fully homomorphic. It turns out that for in a world of commitments and signatures, we can only get leveled homomorphic commitments and signatures. So we have to have an a priori bound on the depth of the computation that we can support. And the reason really boils down to this H matrix here, right? So the norm or the size of the entries of this H matrix actually scales exponentially in the depths of the function f that we're computing. So you have to fix a bound on a function f, and then we have to choose the modulus so that it's much bigger than that bound in order for correctness to hold. So trying to get some kind of bootstrapping for fully homomorphic commitments or fully homomorphic signatures is totally open right now. And finally, another drawback of the existing construction of homomorphic commitments and homomorphic signatures is that we have very large public parameters, right? So if you consider the homomorphic signature scheme, if we want to sign an n-bit message, the public parameters consist of n random matrices, right? And these are very big. Of course, we can compress them by deriving them from a random oracle, but can we do so without relying on random oracles? And with that, I'll conclude. So thanks for your attention. And I guess if we have time for questions, I can take some.
So David, one question.
Yeah.
for the short public parameters, there is some work in the AB world where you can generate your public parameters can be somehow sort of independent of the number of, it's the size of the attributes that you're sort of, and this is very similar to what you're trying to do. So I wouldn't be surprised, I think, you know, not thinking about it too much, not having thought about it too much, I wouldn't be surprised if that machinery can answer your question.
I think that's a very natural direction. So certainly we have AB, I guess this is your work with the speaker, right, that you're referring to?
Right. And that was later, sort of Grant did something better, you know, so one of the two, you know.
Yeah, so it would be interesting to see if a similar machinery can work. So my conjecture is that they should, but I don't think it has been verified. So.
Okay, cool. And if I may ask now that I'm here, it's the second question. So is there a way to formulate your first question, the direct NIZK proof, in a more formal way? And by which I mean the following: if you try to sort of do fiat Shamir, you will embed some sort of a bad challenge function in it, and that would lead to some sort of lattice trapdoors and something like that. So I'm not sure how to think about it as a non-black box use of crypto, because everything you're using here is sort of lattice-like anyway. So it's not like I'm using a sort of one-way function in a.
Well, so for your bad challenge function, the bad challenge function itself is defined with respect to a cryptographic primitive, right?
True, but it's lattice-like. It's a lattice primitive.
It is a lattice-like, but I guess you're doing it twice in some sense, right? You're evaluating the correlation intractable hash function on a lattice-like primitive itself.
Correct, but I don't know how to formally kind of say.
I see.
You know, like,
you know it when you see it. Yes.
You know it when you see it. That's
right. Yeah, that's a good question. So, yeah, I don't have a succinct way, I think, of formally specifying the properties.
Okay, sounds good.
Right. But I guess something that's, I guess as Rand says, it's
you know it when you see it. Okay, that's good enough for me.
Qualitatively different from just applying fiat Shamir.
Okay.
You have a couple written questions, David, if you want to take them now or offline, it's your choice. But after that, I think we'll wrap up.
Okay. Let's see. Yeah, so maybe I'll take those offline. I guess there's one more. So what does it mean for short public parameters? So let's say public parameters that do not need to scale, let's say scale sublinearly in the size of the input is already interesting, I think.